Try to get a sip before it beeped. Sorry. Technology company manufactures scientific calculators with the solar battery. Find the quantity X that maximizes profit. And you got the total revenue and the total cost. So I don't know if you guys have taken like is it BMT, the business class, but you know, profit actually equals and it looks like we're only dealing with 0 to 1100 and 125. But the profit is actually it equals how much revenue comes in, how much money is coming in, and then you subtract the cost it took to produce for production. So P is profit, and sometimes actually they use the letter pi for, because P can also mean something else, but like profit, pi they'll often use as the function. But anyways, that is a moot point. What we're going to do though is we're going to find out that these two functions right here, when we subtract them, they're going to produce the profit function. And let's just keep it a capital P. Okay. All right. So what we're going to do is we're going to take the derivative. So the derivative would just be the derivative of each of these. Okay. And that's a totally legitimate move here. Okay. Because we want to find out the maximum profit means. Okay. Try to think of it like this. Okay. The maximum profit comes when the derivative is 0. Okay. So let's go ahead and do that. We're going to have our derivative of our profit function. Okay. Well, let's just write P of X first. It's going to be this guy, 9x minus 0.004 x squared minus 820 plus 2x. Okay, so notice I put that in parentheses. We're going to subtract both things, and what will happen is we will get, I'm going to put these all in order now, negative 0.004 x squared plus 7x, because 9x minus 2x is 7x, and then we're going to get minus 820. And what we want to do is take the derivative. Okay, so when we take the derivative, let's multiply that by 2. We get 0.008 x, just x, plus 7. Now, what that represents, did I do that right? Plus 7. Yes. Oh, what did I screw up here? Is that right? Okay, let me just double check here. Yep, okay. So we're going to go ahead and now set this equal to 0. Okay, we're going to move that 7 over to the other side. It'll become negative. And now we just solve for x. So x will equal 7. Since they're both negative, it's just going to come out positive. So 7 divided by 0.008 is 875. So x equals 875. So what does that mean? It means that right then, when they sold 875 calculators, okay, they are maximizing their profit. Now, if they sold more calculators than that, then what might happen is that they're starting to go lower because it might cost more materials to produce the extra calculators at this point. And then the profit would actually obviously go down. Okay, so how do we figure out what that profit is? Well, we take the P of 875. We just plug that in, and that's going to be the revenue of 875 minus the cost of 875. Okay, so you just plug in the 875 and see what you get. Let's figure that out real quickly here. 875 minus 0.004 875, but we're going to square that. Okay, let's get the profit. Okay, but the cost is 820 just to get the machines operating, and then, or labor costs, whatever, and then we're going to get that 2 for production. So we're going to subtract those two. Take this guy, subtract this guy, whoops, minus this guy, and we get $2,242.50. Okay, that's the maximum profit for this situation. Okay. All right, and yeah, that is profit in dollars. This is when it happens. Okay. All right, a small balloon is released at a point 150 from the observer. Okay, so he's 150 feet from the observer, and here's our balloon. Terrible balloon. Okay, and it's released 150 from the observer, so they are looking right here. All right, if the balloon rises straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? Okay, so this is our x coordinate. This will be our y because that's height. This is x, and then this will be our z. Okay, how fast is the distance from the observer to the balloon? Okay, this guy, increasing when the balloon is 50 feet high. Okay, so they did give us 8 feet per second. So let's figure out where that belongs. Okay, it says that the balloon is rising straight up. So that means that is a rate of height. Okay, and we labeled that y. And that's going to be 8 feet per second. And it better be positive because obviously the balloon is going up. Okay, and what we're looking for though is we want to know how fast is that distance changing, okay, as it's going up. Okay, so we are looking for dz dt. Okay, and that's the question mark. Okay, so now let's figure out then. They said that y is going to be 50. So what do we know? We know that x squared plus y squared equals z squared. Okay, we are given dy dt, and that equals 8 feet per second. Okay, we're also given 150 equals x, and y equals 50. Okay, so we got those three things, and what we want to find is dx dt. No, I'm sorry, dz dt. Okay, dz dt. And we want to know right at that moment when the balloon is 50. So we wrote y as 50, but we'll just put y as 50. Okay, we know x has to be 150. Okay, well, two things. Let's go ahead, and I'm actually going to change color here. Okay. All right, so two things. Let's figure out when this guy's 150 and this guy's 50, how far is z? Now we can do that just using geometry. Okay, so we know that 150 squared plus 50 squared is going to give us z squared. All right, so let's just keep it all in decimals. It's Sunday. Okay, so I got that when I added those two. I'm going to take the square root of that guy. Let's see what we get. We get 158.11. So z equals 158.11, and we'll just keep that. Okay, so that's z. Now we are looking for dz dt, and let's go ahead and take that derivative now. X squared plus y squared equals z squared, and we've done this before. You can actually look it up in your notes. This guy's kind of a freebie. And what we'll do is we'll notice is okay, remember that with every variable a d something dt is going to pop out because of implicit differentiation. Okay, and we'll notice that we've got an x, we got a y, got a dy dt, we got a z, and we don't have the dz dt, but we do need the dx dt in order for this to work, because we've got to have everything known except one, and then we can solve for it. But in this case we have two. And you probably noticed that if this observer, as long as he's not walking away, then this dx dt is actually 0. So he is not changing at all. Okay, so what we could do is go over here, and you might have seen it right in the beginning that dx dt is actually 0 because he's not moving. Now he could have moved, and as long as we knew how fast he was moving, either towards the balloon or away from the balloon, we could solve it still, but because he's just standing there at 0. So that kind of helps us out. This whole thing right here is going to go to 0. Okay, so that's cool. Let's go ahead then and plug in the 2 times y, which we said was 50, and that's our dy dt, and that's going to equal 2 times 50 times dy dt, which is 8, and that's going to equal 2z times dz dt. Now z we said was this guy. Now we're going to have to divide by this, so why not just do this? 158.11, and that's going to equal dz dt. Now just kind of, I'm running out of room, but I could have filled it in there, but I still am going to have to divide by it. So yeah, let's punch that out, and that's going to be how fast this thing is changing. And that just, to me, I'm always amazed by the power of calculus and our ability to figure out these moving pieces. 2.53. So dz dt, 2.53, and that kind of gels with me because that's going to be feet per second, which means that distance is just getting bigger, right? 2.53 feet per second. So even though he is rising faster, that distance is changing at between the observer and the balloon is changing at a slower rate, okay? Because he is 150 feet away. All right, so that's really cool. And let's do this last one for this page. Sand is falling into a conical pile. Okay, always draw a picture here. Okay. The cones are always funny because I don't know if there's ever, well, no, it would be a perfect cone, you know, if it's fine sand. Sand is falling into a conical pile at a rate of 12 cubic feet per second. Okay, so the volume is getting bigger. The diameter of the pile is 4 times the height. Okay, so the diameter is 4 times the height. At what rate is the height of the pile changing when the pile is 8 feet? Okay, so what they said is that this guy is, well, first of all, what do we know? We know the volume of a cone, which is 1/3 pi r squared times the height. Okay, and we can take that derivative, and what you'll find is that the r is there, and we do not have a radius changing here. The best thing to do, okay, is, because the radius is going to change, it is changing, but that information is not provided, so we've got too many variables. We've got to write r in terms of h, because we are looking for dh dt. Okay, so we need to know that. So what we got to do is pull out the r and put in an h. And what they did is they gave us a clue here that the diameter is 4 times the height. Okay, so what we got to do is carefully, and these are always tricky for me. Okay, the diameter is 4 times the height. So diameter equals 4 times the height. Now, what we're going to do is we're going to replace d with half of d. No, we're going to replace it with 2r, because 2 radiuses equal 4 h's. Okay, so now what we got to do is say we're going to divide both sides by 2, so we get r is 2 h's. So this means that we're going to replace this volume formula with our situation, and it's going to have 2h squared times h. Okay, so we've got that r out, so we can replace it with a geometric relationship that is kind of given to us already. Otherwise, we'd have to know how the radius is changing. Okay, somebody had to have figured that out. And you can figure that out if you have the right tools on site. So what are we given? We're given that dv dt, the rate at which this pile is growing, is 12. Okay. We also know that the height has to be at exactly 8. Okay, so we could actually put that height equals 8, or we could just put at height equals 8. All right, so let's get this derivative here. dv dt equals, oh wait, you know what? I'm sorry. I'm going to have to do the v, because I got to square this out here. V equals 1/3 pi. This is going to be 4h squared times h, which is going to give us 4/3 pi times h to the third. So that's cool. That's actually a lot easier. When we do dv dt, we'll take that derivative. The 3 comes down. Now pi is just pi. He's not a variable. So he's just a number, and he's going to stay there. But that 4 will remain. We'll get 4 pi, and then the h will just drop a degree. And that's very clean. Okay, very, very clean. And we're just going to go ahead and times dh dt. He's got to pop out, right? Okay, so we got to find this guy. And we have this guy. So we know that that's going to be 12. And we're going to divide by all of this. So 12 divided by 4 pi, and h is got to be 8. Okay. And that's going to be our answer once we figure out what all this mess is. So we're going to draw a little arrow here. dh dt equals, well, let's see, that's going to be 3. And so 3 divided by 64 pi. We could actually just leave it right there. Okay. That is a perfectly fine answer. And if you wanted to know the decimal, you could just do it that way. All right. And let's make sure that we do write our units. This is, he's changing by height. So therefore, it's going to be feet per second. Okay. It's not volume, it's height. So that's going to be a linear measure going upwards. Okay. All right. Long video. Whew. But that's related rates for you.